Great. So this is our first seminar in a hopefully long series of seminars. And our goal is in general talk about like topics related with climate, weather, and like all of this stuff in the particular context of Africa. And today to open the series, we have the Gray to talk about the flood forecasting effort at Google Research. So Gray is currently a senior research scientist at Google. Prior to joining Google, he was assistant professor at a couple of universities like UC Davis and University of Alabama. He was also a research scientist in NASA, UMaryland, and a lot of cool institutions. He did his PhD and master's at University of Arizona, and he had worked in a lot of really cool projects related with weather and climate. But I have no idea, but like he worked from physics-informed machine learning to quantum annealing for carbon monitoring, and now he's mainly focused on flood forecasting. So yeah, you can take it off.
Yeah, super cool. Thanks. And thanks for having me. And thanks everybody for showing up. This is great. Really, really nice initiative. Got a lot of attention on LinkedIn. So this is really positive sign. Thanks again for hosting. So I guess I need to start my screen. Let's do here, Chrome tab. Great. All right, everyone can see it, I assume, because I can see it. Yeah, so feel free to jump in with questions. Questions are really welcome. I'm going to try to leave some time at the end for questions. But as far as I'm concerned, unless the organizers feel differently, please just ask anything that comes to mind. I'd be very happy to talk in depth about any of these things. So there's a little bit of, I mean, we have to go through this in like 45 minutes. So we're going to gloss over a few things. So anything that you're interested in, please just let me know. So the title of this talk is Global Prediction of Extreme Floods and Ungauged Watersheds. And that title is the title of our recent paper, which was chosen by the journal that we published the paper in, not by us. I think that the real message of this talk is how we use machine learning for flood forecasting. So that's kind of what we're talking about. And the reason that, so I work at Google, the reason that Google is doing flood forecasting is simply because people come to Google for information about floods. We get lots of hits a year. Is it flooding in a particular area? Is it flooding around me? Is there a flood warning near me? Things like that. People Google search this all the time. People come to Maps for information about Google Maps for information about what's going on around them. And we would like to be able to provide information about floods on Google Maps. And we would like to be able to provide information about floods through push alerts in countries where that's allowed and where the governments of those countries invite us to do push alerts to cell phones. So for example, in the United States, I live in California. In the United States, the National Weather Service in the United States, when there's a flood warning, they'll push an alert to your phone. It'll beep. It's unsolicited. You don't do anything to get it. It just comes to your phone because it knows you're in the area. And Google has the ability to do that in places where governments want us to do that. So this is the reason why we're doing flood forecasting. The other sort of aspect of the motivation is that floods are the most common natural disaster in the world. They're not the most, they don't cause the most fatalities and they don't cause the most economic damage, but they're the most common natural disaster in the world, and they affect more people per year than any other type of natural disaster. So in this study between 1995 and 2015, about a 20-year period, the UN Office of Disaster Risk Reduction found that about a little over 50% of people that were affected by natural hazards were affected by floods, and that's billions of people. The other thing that's important to understand is that early warning systems are useful for preventing both fatalities and economic infrastructure problems for all types of natural disasters, including floods. So in particular, the World Bank estimated that early warning systems are probably the most cost-effective infrastructure investment in climate resilience. And the idea is that you can reduce fatalities from floods by about 8 times with high quality, high precision flood warnings versus places in the world that don't have flood warnings. So the challenge is, how do you get flood forecasts and early flood warnings to people around the world that need it the most, that have the most exposure and the most vulnerability to floods? So the challenge in doing that is setting up models that actually predict floods. That's the first step in the process. There are other parts of the challenge which are related to last mile delivery. How do you get flood warnings into the hands of people that need it? But just at this sort of first step, when we're actually trying to forecast floods, the challenge is that places in the world with populations that are most vulnerable to floods are also correlated with places in the world that have the least amount of data related to river flow and floods and things like that. So what you're seeing on the screen now is a plot that shows a correlation between the GDP of a country and the total years of stream flow data record in a country. So we train our hydrology models, we calibrate hydrology models on stream flow data records, and stream flow data records are critical for calibrating models that are able to give accurate forecasts. It's really, really difficult. Before we worked with AI in this space, these classical hydrological models that are used for flood forecasting, the way that they're able to provide accurate flood forecasts is that they're calibrated to a particular location where they're going to make predictions. So if you have a particular river or a particular watershed or a particular area where you have you want to offer flood warnings, you have to have historical data in that area to calibrate your hydrology model. And we're talking about models that are not AI, not machine learning models. These are just traditional physics-based hydrology models that try to simulate the way that water moves through the landscape. And the challenge is that, so there's sort of what's not shown on this slide is there's a correlation between GDP in a country and sort of the vulnerability to flood risks. So that correlation is sort of assumed to be known in the background of what we're talking about. But what this plot shows is that the amount of data that's available for calibrating flood forecasting models is sort of inversely correlated with the vulnerability of the population in an area. So what we need a model that generalizes to locations or situations where we don't have observation data. And that's the reason why we like machine learning and AI in this space. So what did we do to sort of address the problem? We went out to the different government and intergovernmental agencies specifically, and we got all the data that we could find related to this problem. So the problem that we're going to talk about today is predicting riverine floods, so floods that are caused by rivers that overflow their banks. And so the main data source that we're going to talk about using today is the data about the amount of water that's in a river. So if you look at the map here, this shows locations in the world where this Hydrosheds program, so Hydroshed has stream flow data. Hydrosheds is a program that's sponsored by the United Nations, the World Meteorological Organization, and its job is sort of to collect all of the world's stream flow data, except I got it wrong. It's not Hydrosheds, it's the GRDC, apologies. The Global Runoff Data Center collects the stream flow data around the world. And so this map sort of shows where the Global Runoff Data Center has stream flow data and how much, how many years of record they have in a particular area. And you can notice that there are geographical biases. And so the question is, how can we take all of this data, train an AI model, and then in a way that allows us to apply that model anywhere in the world, even in the places on this map that don't have data? So basically what we're going to do is we're going to think about the relationship between what causes floods. So we're going to talk about we're going to think about what causes floods. And again, we're confining our discussion today on, just to keep things simple, on floods that are caused by rivers overflowing their banks. So we're not talking about coastal floods, which are caused by storm surges. And we're not talking about flash floods that are caused by rain hitting the ground and not being able to drain fast enough before they cause problems. We're talking about these kind of major floods where there's so much rain and the rain occurs in this situations that are just right so that rivers overflow and sort of flood the areas around them, the floodplains around them. So what we're going to think about is the way that rainfall turns it to stream flow, and we're going to try to model that process. So what do we need in order to model that process? We need sort of three things. We need weather data that includes the amount of rainfalls that's going to fall in a particular area. It includes the temperature of the area, because hotter temperatures mean that more water evaporates and less is available for overflowing rivers. We need things like humidity, wind speed. All of these things have sort of minor effects on the total amount of water that's going to make it to a river. So we take all of that kind of data from weather forecasts. So we take weather forecasts from several sources. One is the European Center for Medium Range Weather Forecasting, which is sort of one of the main global weather modeling centers in the world. We also get weather data from GraphCast, which is Google's weather forecasting model. And we get some precipitation data from satellites. One in particular is this NASA product called IMER, which measures precipitation from a satellite that's orbiting Earth. And then we also, so that's the first kind of data we need. We need weather data as inputs. Rivers overflowing their banks are caused by weather events, and so we need data about weather. We also need data about the sort of geography of the watersheds. So geography includes the climate of the watershed. We'll get to that more later, why climate is important. The geology of the watershed, the sort of rocks and soil types, the vegetation that's in a watershed. Watersheds with more vegetation means that less water will make it to the rivers because more water will be absorbed by vegetation. And then information about human impacts, so anthropogenic effects. That's like how much of the watershed is paved due to there being cities in the watershed, how much agriculture is happening, how many people live in the watershed. These have a lot of effects on how much water makes it to the river. So we collect data about all these things in every watershed globally, along with the weather data. And then finally, the third type of data we need is that stream flow data, which will be the target data that we use for training. So this is sort of a list of the data sources that we have, global data sources that we have over time. So this is, we have historical data for training, the sort of light green bar at the very bottom, GRDC streamflow target data. That's the streamflow data from the map that I showed you earlier. And that's the target data, the data that we're going to use to train the model to predict. And the other blue bars are the data that we're going to use as model inputs. Some of our model inputs are only available in the past. They stop at 2023. Actually, ERA 5 land is one of our main, that's a weather data product. That data product stops about 2 months in the past. So it's constantly being updated, but it's always about 2 months lagging behind real time. So we can't use it to actually make forecasts, but we can use it to train our model, and we do use it to train our model. So what we do is we take the European Center for Medium Range Weather Forecasting, this ECMWF organization that produces global weather forecasts. They run a couple models. One is this ERA 5 model, which runs way, way back in the past, and one is their real-time forecasting model, which is sort of the third bar right here. And this is their forecast model. So we do some masking to sort of be able to combine these two data sources so that we get a long record for training, and we also get real-time forecasts so we can make predictions now up until a few days in the future. By the way, our predictions go up to 7 days in the future. We'll talk about that in a minute. We'd also take data from the IMER satellite, the IMER satellite-based data. IMER is not a satellite. The satellite is called the GPM, Global Precipitation Measurement Mission, but IMER is the data product that comes from that satellite. That's from NASA. And then we take some ground-based rainfall data also that's available both in historically and in real time. We bring these in, we combine them in ways, sort of hopefully intelligent ways that we've thought about a little bit. We do training up until about 2023, and then we make predictions in real time. So we run the model twice a day. It makes forecasts 7 days into the future. Okay, so what does the model actually look like? We use an LSTM-based model. So this is a little surprising. We have a joke in our group that may be true, may not be true. I don't know, it's probably not true, but we're one of the only groups at Google that are still using LSTMs. Most LSTM applications have been replaced by transformers, but for our particular problem, this modeling the relationship between rainfall and stream flow, LSTMs work really well. And the reason that they work well is because they're Markovian. So the watershed is a physical system. The behavior of water as it hits the land and then runs off into a river, that's a physical process. In order to model a physical process, what you need is the current state of the system plus any new boundary conditions. The boundary conditions are our weather data. That's the precipitation that comes into the watershed. So you have this current state of the system and the current rainfall, then that's all you need to make the prediction for the current time step. And so that's different than a transformer. A transformer will look at let's say a time series of data, let's say a sentence let's say you're using it for natural language processing, that your time series data in that case will be one sentence or one paragraph translated into the same meaning in a different language. So time series to time series. So transformers, they're non-Markovian. They can look back in the past and they can learn relationships that are non-sequential in time. But Physical systems are sequential in time, and so the LSTM works really, really well for this type of modeling. I actually just explained this slide, so that's okay. The way we apply this model is we apply it per watershed. So what you see on the left here is a river basin, a drainage basin for a large river. That's sort of the gray area. And then each area with a different color is a smaller subset, a smaller sub-basin or sub-watershed that feeds into a smaller river that ultimately feeds into the large river that drains out of that polygon on the right-hand side. And what we do is we apply our model at each one of these sub-watersheds. So everywhere that we have a location for a streamflow gauge, so everywhere we have streamflow data, we take the whole drainage area upstream from that streamflow gauge and we apply the model to predict at that particular location. So this is kind of what our geographical maps look like when you zoom into a single river. We apply this LSTM model. And then the other important thing that's useful to understand is how we do forecasting. So the problem with forecasting is an LSTM model, so just I assume most people know, but an LSTM model is a time series model. It takes a time series of inputs and it produces a time series of outputs. So our time series of inputs are a time series of weather forecasts, or weather data, sorry. And the time series of outputs are a time series of streamflow data, the streamflow being the amount of water in a river. We run these models for 1 year. So what we do is for every prediction, if we're making a prediction today, we run the model for 1 year in the past up until today. So it gets all of the weather history for 1 year in the past, makes a prediction for today. And in fact, then it makes a prediction for 7 days in the future. The problem is that that year that we run the model in the past, we call that spin up. So that spin up period for 1 year in the past, we use historical weather data to run the model for that spin up period. And that just gets the model sort of into the climatology. It kind of understands the current state of the watershed so that then you can say what happens when this new weather, this new rainfall that's been forecasted for tomorrow, what will that do? What kind of is it falling on a watershed that's already wet or a watershed that's dry? These sorts of things. The problem is that the historical weather data for the past 365 days has much lower uncertainty. It's much more accurate data than the weather forecast for the next 7 days. The uncertainty for the weather forecast is for weather that's going to happen in the future is much higher than the uncertainty for weather that's been observed in the past. So what happens is you can't use the same time series model to model the past and the future. So we're going 365 days in the past, 7 days in the future. The problem is that the weather forecast data for that 7 days in the future has drawn from a different probability distribution, a different uncertainty distribution than the weather data for the 365 days in the past. You can't, that would be kind of a distribution shift in the inputs, which is a big no-no in machine learning. So you can't run a model just sequentially in time through this whole forecast, this whole period, past and future. So what we do is we use 2 LSTMs, one for the past and one for the future. The past is this sort of blue LSTM here. These blue boxes are sort of the LSTM cells that run from 365 days in the past up until today. And then we hand off the state of the model, the outputs of the model, sort of the cell state and the hidden state of the model to initialize another LSTM that runs for 7 days into the future. And that's how we deal with this distribution shift. Okay. So what does this look like in practice? Just to start this off, we have a paper that was just published last month on the results. We trained this model globally, applied it globally, and then we compared it to the flood predictions coming out of the European Center for Medium Range Weather Forecasting, which is sort of the largest weather agency in the world. So we used them as our baseline, and our question was, does AI offer improvement over the forecasts that they give, specifically in places without training data, without streamflow data for training? So what we did, so in order to measure that, we had to divide the world, all of those gauges up, the streamflow gauges up. I'm going to go back, all of these locations up into training and test sets. So we did k-fold cross-validation with 10 folds. So what that means is we took 90% of these data points selected randomly. We trained on those, and then we tested on the other 10% of those data points, and we did that 10 times. So we tested on every data point out of sample, meaning predictions at every one of these data points made by a model that's never seen that data point, that location during training. So what we get is something like 5,000 watersheds worth of data that we can compare to observed data, and the predictions over all 5,000 of those watersheds for a period of about 40 years are all out of sample, in the sense that the model making predictions at each one of those locations has never seen training data from that location. And what happens is we calculate metrics based on return periods. So return period, a return period is how often we expect an extreme event to happen. So we care about high stream flow events. A 2-year return period means that this is the highest level a river is expected to reach on average once every 2 years. It's expected to be the expected value of the time between these events, 2-year return period events, is 2 years. So if you have a location that floods annually, you probably care about a 1-year return period event. If you have a location that floods on average 2 years, every 2 years, you want to care about a 2-year return period event. If you have a location in the world that floods on average once every 10 years or once every 50 years, you care about a 10 or a 50-year return period event. So what we're doing is we're quantifying the skill of predicting these large stream flow events defined by return periods. And we're going to look at the precision and the recall of our model, and then the ECMWF model, which is called GLOFASS. GLOFASS, if you see that sort of label on the bottom on plot here, GLOFASS is the Global Flood Awareness System, and it's produced by this European Center for Medium Range Weather Forecasting. And we're going to look at the predictions over a 7-day forecast horizon. So lead time means how many days in the future we're making predictions. And on the y-axis here is the F1 score, which is the harmonic mean of precision and recall. It's basically the average of precision and recall. Our precisions and recalls are about the same, so taking the average makes sense so that you can get the information on one plot. And basically the takeaway is that we get accuracies, precision and recall accuracies over both 1, 2, 5, and 10-year events. All that's shown here are 2-year return period events, so floods that happen once every 2 years. But this conclusion is the same for basically all return period events up through 10-year return period events. We get accuracies up to about 5-day lead time that are on average as equal to the accuracies of the current global model. That's the GLOFASS model today. So if GLOFASS is predicting what the stream flow is today using only observed weather data from the past, they get this particular accuracy. And we get that same accuracy up to about 5 days in the future, meaning that the current global flood forecasts that are currently available, we're able to extend the lead time on that level of accuracy by about 5 days. And that's sort of everywhere. That's sort of everywhere in the world. And specifically, this is using a model that's trained in locations that is predicting in locations where it has never seen any training data. So again, we have a geographical bias because we can't actually test the model in, for example, Ethiopia. But what we can do is we can play this cross-validation game, so saying if we don't have any data in a particular area, what is the skill in that area? And this kind of gives us a sense of what the expected skill is in places without data. The second major conclusion is that this machine learning approach has accuracies over larger events. So our accuracies over 5-year return period events, which are larger than 1-year return, is about the same as GLOFASS accuracies over 1-year return period events. So we can predict larger floods with similar accuracy to the current state of the art predicting smaller floods. And that's a big deal because larger floods are typically harder to predict. So the question is, if you look at this plot, the top plot now, and this shows where the machine learning model performs better than the GLOFASS model, the current state of the art. Green is where the machine learning model performs better, and pink is where the current state of the art performs better. And it's about 80% of the locations on here are green, but about 20% of the locations on here are pink, meaning that the current state of the art performs better than the machine learning model. And so the question is, well, if that's the case, why not run both models and use one model where it's good and the other model where it performs better? So then in order to do that, what you need to be able to predict where each model will perform better. So we created a little random forest model, just a really simple database model to take in these geographical features that I mentioned earlier, like climate, vegetation, soil properties, geological properties, and anthropogenic properties. And those are sort of those properties characterize the watershed. And so we use those to predict where each model will do better than the other. So if we could find systematic patterns where one model performs better than the other, then we could learn where we want to run one model versus the other model. The problem is there are no systematic patterns. So what you see here is that the model just predicts that our predictor about which model performs better, our classifier that predicts which model performs better in a particular location, just basically always predicts that the AI model performs better. And just, I'm not going to go into details here, but this was done, this model was trained with recognition of class imbalances. It was, this is a very rigorous and robust model, and there just isn't any systematic pattern in where one model performs better than the other. So we can tell, however, where a particular model will perform well versus where that same model will perform poorly. We are able to train classifiers that understand that. So what we do is we feed those same catchment attributes, those same geographical features into a classifier and predict the skill score of one of the models, either this GLOFAST model or our AI model. And we can see that it classifies whether the skill score is going to be above average or below average fairly well. It gets it about 2/3 of the time. And that's true for both models. And that means that both models are struggling with making predictions in certain areas of the world, and they're struggling with the same areas of the world. Okay, so what's driving that? The main driving factor, the main thing that makes it hard to predict floods is aridity. Aridity is the sort of arid basins, arid locations in the world are places that are dry. Humid locations are places that are wet, and it's much harder to predict floods in places that are dry. The reason for that is that when there's not a lot of rain, floods are usually driven by a single rainfall event. So the history of the location doesn't matter nearly as much if it's an arid location. It's just how much rainfall is coming, and is that enough to cause a flood? And the problem is that rainfall data is quite inaccurate. It has high uncertainty. And so if the only thing that's driving floods is rainfall, and you're relying completely on this sort of high uncertainty data source, rainfall data source, to make predictions, it's very difficult to make accurate predictions. Humid basins, where the models both perform pretty well, what happens is, I'm going to show you a map of where these models perform, where the AI model performs well and poorly. So this is sort of the expected skill score, precision and F1 score, which is precision and recall. This is the expected skill score over the world, derived by this classifier. And basically what you see here is humid basins. What happens is there's sort of two factors that go into whether something area floods. One is the current rainfall, if it has to rain enough to flood, but it also has to be already moderately wet. So if there's a lot of rain that falls on a dry catchment, then it's less likely to cause a flood than a lot of rainfall that falls on a catchment that's already seen a lot of rain recently. And so this means this sort of time series of weather data matters much more than sort of instantaneous weather data. And so the model has a chance to sort of overcome the uncertainties in this sort of time series of weather data. Any individual estimate of rainfall doesn't matter as much as the whole time series of rainfall. And so it can kind of regress to the mean and kind of get an idea of whether it's above average or below average at this point in time. So these are based on these sort of understanding of the system and understanding what's driving skill in the models, these are the areas of the world where we expect the model to perform well versus perform poorly. And you can see this model map was produced by that classifier, that skill classifier, and you can see that it follows the models are expected to perform well in humid areas and not in arid areas. So future work should look at how to predict floods in arid locations. Okay. Let's see. I have a lot more here, but I'm probably going to stop and just say, what time is it? Is it?
No, it's,
oh,
you have plenty of time.
Oh, sorry. I'm half an hour off of my, perfect. Okay, cool. Okay. So there's a couple other things that I want to talk about. So we take this work around to academic conferences, and we talk with hydrologists, people that are specialized in this area, and we get a lot of feedback from people that have spent their careers doing flood forecasting and hydrological modeling. And this feedback is really important to understand, if to build trust in the AI systems and to understand if there are any deficiencies. And one of the main pieces of feedback that we got is, well, what we really care about during flood forecasting is these extreme events, which is what we've been talking about this whole time, but specifically extreme events that are rare. So the problem is the events that we care about, even in locations where we do have data, are relatively rare. We care about these peak flow events, not the sort of day-to-day amount of water in a river. And if you have a training data set that doesn't, for example, contain a 50-year flood or a 100-year flood, how is the model going to be able to predict a 50-year flood or a 100-year flood? So what we did is we divided our training data set up so that we only trained on portions of the data set without these extreme events in it. So we took all of the data that we had, we divided it up year by year, location by location, and we trained only on data from years where there was no large flood. So where the largest flood stream flow measurement would be a 1 to 5 year return period event, and then we use that model to predict return period events that were like 5 to 25 year return period events, 25 to 50 year, 50 year to 100 year return period events. And this is and then what you're looking at here on this graph is the skill score on the y-axis. So the return period on the x-axis, we trained on these 1 to 5 year return period data. So this is the performance over the data that we trained on. And this is the performance over the data that we didn't train on. And these are pretty extreme floods, 50 to 100 year floods, 100+ year floods. And what we're looking at is the percent error on the prediction of the highest flow event in that data record. So lower is better, lower error is better, it's a percent error. And you're looking at the percent error on the absolute peak flow. And so the peak flows get higher as you go further left on or further right on the x-axis. And we're comparing 4 different models. We're comparing our machine learning model, the LSTM. We're comparing a variant of the machine learning model that I'll talk about in a minute called the mass conserving LSTM. Forget about that for the moment. And then we're comparing that with the 2 operational models that are used for flood forecasting in the United States. The Sacramento soil moisture accounting model is the model that actually is used if someone in the United States gets a flood warning sent to their cell phone. That flood prediction comes from the Sacramento soil moisture accounting model. And then the National Weather Service is testing a new model called the National Water Model, which is this model in gray. The model in gray has a caveat because it's actually not trained out of sample. It's actually predicting in places where it's seen all of the training data, whereas that's why it's in gray. Whereas all the other models are predicting in location, or they're predicting in this sort of train split where it's only seen small events and not seen these large events. So what we're asking is, as we go to larger and larger events, how do these skill scores decrease? So it's going to be harder and harder to predict as you get further and further out of sample, but how much do we lose? And so what we want to compare is the blue model versus the green model. So the green model is the model that's actually used for flood forecasting in the United States. The blue model is our model. We expect to lose skill as we go to more and more extreme events. And the question is, does the machine learning model, since it is based only on, it's a database model, it's based only on regression with these sort of, it's never seen any data with 100-year return period events, does it go off the rails and produce bad predictions that are worse than the sort of physically based models, the physically realistic models that are used by the National Weather Service? And the answer is no. The physically realistic models, the Sacramento model and the Sacramento model, at least, not the National Water Model, loses skill faster than the machine learning models, even when the machine learning models have never seen these very, very large events. The National Water Model is a different story, but again, it's not a direct comparison because it's actually been calibrated on 100-year flood events. So of course it's going to perform better on 100-year flood events. It's still worse, by the way, even though it's been calibrated on 100-year flood events, it's still worse than the machine learning model, which is worth pointing out. It does a little bit better on some of these intermediate events, but again, it's been calibrated on all of the data. Okay. One of the other really interesting things that's happening in here, and this is sort of just a slide to pay homage to or provide a little nod to explainable AI. We get a lot of comments from people that have spent their careers in working on flood forecasting. We get a lot of comments about, well, why should I trust your model? It's a black box. These AI models, machine learning models, are just a black box. We're used to working with physics. So we spent a little time trying to explore the models and understand what they're doing. And this is one of my favorite results from that work. Basically, this experiment took 3 different precipitation data sources, fed all 3 into the model at the same time, and then we asked we sort of asked the question, which precipitation data source is the model listening to the most? So which precipitation data source has the largest influence over the prediction that the model's making? And the way that we measured that was with integrated gradients. So we just measured the sensitivity of the model to each of these different input data sources. And the technique is integrated gradients. So you just take the sort of the partial derivative of the output with respect to one of the inputs. You use backpropagation to calculate that partial derivative. It's a pretty, there's more to it than that, but that's basically the gist of it. And it tells you sort of the sensitivity of the model prediction to each of these three different precipitation data sources. So what you're looking at in this plot are blue, green, and orange. It doesn't matter what these precipitation data sources are. They're NLDAS, DAMET, and MAUER. They're just three different groups, organizations that produce different precipitation estimates around the United States. We're going to call them blue, green, and orange. The color on the map, so all the dots on the map are locations where we have streamflow data in the United States. And the color that's shown for each of those dots is the precipitation data source that the model listens to the most in that location. And remember, this is one model trained on all of this data. So it's not a separate model for each location. It's one model trained on all of this data. And you can see that the model learns to listen to different data sources in different ways. So the three columns are different parts of the streamflow prediction. The left-hand most column is just the whole streamflow prediction over every prediction it's making over the whole time period. The rising limb is the onset of a flood, and the falling limb is the recession of a flood. So how quickly the flood recedes after the event. So it listens to these different precipitation data sources, to different amounts in different locations, and under different hydrological conditions, whether the flood is coming on or whether it's going out. And that tells us that the model is really able to learn sort of systematic patterns in the errors and the error distributions of these precipitation data sources. This is really interesting to me, coming from a hydrology background, because the way that you would have to do this without machine learning is you would have to train a separate model for each of these data sources and a separate model for each of these locations. And I'll get to that in a minute if we have some time. Yeah, so this work there's a lot of papers on this. I'm going to skip this, but if you're interested, there's a lot of papers that we wrote about this. And the last thing that I'm going to talk about is mixing physics and machine learning. So the last major comment that we get from people, professionals, flood forecasting professionals, is they really trust their physical understanding, their understanding of the physics of a watershed. So when you use machine learning, you remove all of the understanding of physics from the problem. And we took this complaint seriously because people really, these forecasters that make operational forecasts in different places around the world, they really think about how rain is moving through the watershed to turn into stream flow. So one of the things that we did is we said, okay, what's the most basic physical principle that drives this process, this rainfall runoff process, rainfall streamflow process? And the most basic important physical principle is mass conservation. So water is neither lost nor destroyed. All the rain that hits the watershed has to go somewhere. It doesn't have to go to streamflow. It might go to evaporation. It might go to groundwater. It might be used by humans. It might be used for agriculture. It might be used by plants, whatever, but it goes somewhere. And so we don't want the model to create or destroy any water. So what we did is we created a version of the LSTM that obeys conservation laws. And there's a little bit of complexity under here. I'm probably not going to go into the details, but there's one really, really simple trick. So this is an LSTM cell. There's one really, really simple trick in that every little neural network, every activation layer within this larger deep learning network, we normalized it and multiplied it. Then you multiply it by the value that you want to conserve. So in our case, we want to conserve the amount of water that comes into the watershed as precipitation. So every layer in our deep learning network, we use a sigmoid, a tanh, whatever, we normalize that layer. We take the L1 or L2 norm of that layer so that all of the outputs of that layer sum up to 1. And then we multiply all of those outputs by the value of the quantity that we want to conserve. And so now if you sum up all the outputs of any activation layer in the neural network, they always sum up to the quantity of the value that we want to conserve, which in our case is precipitation. You feed that into the model everywhere, and the model always knows exactly how much water is in the system. I'm not going to get into more detail than that, but that's the basic intuition without really thinking through the mechanisms of an LSTM. You can play that trick, by the way, in any deep learning network. You can do this normalization multiplication trick to conserve quantities, mass quantities, momentum quantities, energy quantities. We used a group used this model that we created that to track cars on roadways. So one of the problems with some AI models is that if you try to use them to predict traffic, cars will disappear and appear out of thin air because there's no guarantee that it will conserve the numbers of cars on the road. This model will always conserve the total number of cars on the road, so no cars will disappear or reappear. And it's this little trick that you can apply to sort of any activation layer in any machine learning model. So we applied it to the rainfall runoff problem. And I'm not going to go through this plot. I'm just going to say the answer in words. It actually hurts. We get worse predictive skill when we try to conserve water than when we don't add the physics to the model. And the reason is very simple. I'm going to sort of spoil the reason, but the reason is because there's error in the rainfall data. And if you treat the rainfall data as the actual true amount of water going to a catchment, then you're going to get the wrong amount of water. The rainfall data itself is wrong, so you're going to get the wrong amount of water coming out. And what the machine learning models can do if you don't force them to obey the mass conservation is they can learn systematic patterns in errors in the rainfall data, and it does that. And that actually adds skill to the model. So forget about what's shown on the screen. That's just a way of showing that adding the mass conservation to the machine learning model causes a very small decrease in skill. And yeah, I am going to leave it, and I'm going to say one more thing. We run this model that I talked about. We run it globally. We run it operationally. You can go to the Google Flood Hub, which is here, g.co/Flood Hub, and you can get our 7-day predictions in real time anywhere in the world where we offer predictions. So this is a map of places in the world where we make predictions. Actually, we make predictions in many, many more places, basically everywhere, but we only show places in the world where we've hand verified the predictions. So where a human has gone in, looked at the predictions for the last 40 or 20 or 10 years or however much past data there is at a particular location, verified that the model's doing well, calculated a whole bunch of skill scores, made sure those skill scores make sense based on what they're seeing, and they look at all the predictions, and then they check yes or no. We check yes or no on a spreadsheet, and then if we decide that the model is good in a particular place, then those predictions show up on the Flood Hub here. So you can go here and see all of our predictions. Now, within the next month or two, we'll have a version of the Flood Hub that doesn't have that verification process and just shows all of the predictions everywhere. We call that expert mode because it really should only be used by people that are experts and know that there's some error in the predictions. But these are the locations in the world where we're comfortable releasing predictions. With the exception of India, we also release predictions in India, but they're not shown here at the moment. And so what you can do, what this is showing, green are rivers in the world where there's nothing exciting going on, or where our model thinks there's nothing exciting going on. Red is where we think there's an extreme flood, which is a 10-year flood event. Orange is where we think there's a smaller flood, which is a 2-year return. Red is 5-year, orange is 2-year. Yellow is 2-year. So these are where we think there's moderate potential for flood or extreme potential for flood. And you can zoom in on one of these dots. So here we're zooming in on a place in California, looking at one of these red dots. You can zoom in and kind of see exactly where that dot exists on the river. And then in some places we provided inundation maps. So a map that shows where we think the flooding will occur. In fact, you can see that right here. So these water bodies here are actually not water bodies. There are predictions about where water will overflow the banks of the river and cause inundation. Yeah, so that's the Flood Hub, and thanks.
Great, thanks.
Yeah.
So I think we're open to questions. You can put your question in the chat, or if you feel like if you want to ask it just by voice, you can also do it. I have 2 questions actually.
Yeah.
So when return period is like a common topic, like you use return periods to describe everything, but climate change are making these floods more common. So how the climate change is affecting the return periods, and what are the implications when you are building the platform and the models?
Yeah, it's a great question. So if you're, let's say that you're not doing flood forecasting, let's say you're doing pricing for home insurance. So what you care about is not whether it's going to flood in the next 7 days, but the risk of flooding over the next 30 years, right? There, it's really, really important to understand how the potential for extreme events are going to change and how the return, which means how the return periods change. That's how the return periods change is another way of saying, are more extreme events more or less likely to occur in a particular area? So does that lower or increase or reduce the risk of flooding over the long term? We're talking decadal scale. So yeah, as climate change, so what we see in our data is if you calculate return periods on the last 5 years, they're quite different than the return periods on the last 40 years ago, that's for sure. But what we're using return periods for is just a marker, just to say, this is just as a marker to say, this is an extreme flood, a moderate flood, like a moderate event, a very extreme event, nothing. So we calculate on all the past, these metrics on all the past 40 years of data, and then we just use them as markers for warning levels and danger levels. There's nothing in flood forecasting. If we're looking 7 days, then climate change isn't going to change the return periods now versus 7 days in the future. But as we move, like if we're still running Flood Hub in 10 years, we'll need to then go back and recalculate all the return periods again and say, how much have these changed, have people's expectations. A return period is useful because it sets expectations for someone on the ground. Is this something that we see once every 2 years? Is this something we see once every 5 years? And those expectations will change, but they'll change on like the yearly and decadal scale. And yeah.
I have another question, but I also see that a couple of persons put questions in the chat.
Cool.
So let me take some from the chat. So the global Google LSTM model predicts stream flow in Ungauged underobserved northern. I think it's better if you read it.
Okay, cool. Let me just,
Okay.
I'll read it. All right, cool.
Yeah, I'm really bad at reading in English. Sorry.
Mohammed says, the global Google LSTM model predicts stream flow in ungauged, underobserved northern watersheds. I'm curious about the model performance when ice is present in rivers. Does the model incorporate ice information during freeze-up or breakup periods to predict ice-induced floodings, which could reach the level of 10 or 25-year return period events? So that's the first question. The answer is we don't look specifically at ice in rivers. So we don't have a satellite. We don't use satellite data that looks at the formation and the melting of ice in rivers. The model does learn to predict both snow and ice melt sort of implicitly. And we do have a paper that describes how it does that. It's really actually kind of fascinating. If you train the model just on precipitation and temperature as inputs and stream flow as outputs, one of the states in the model tracks snow accumulation with R-squared scores of like 80 or 90%. Yeah, and it has to learn, something in the state of the model has to learn the amount of storage of water in a watershed and how that storage reacts to temperature. And so we can actually we can find and then extract that particular state of the model, and we can correlate it with the observed or modeled snowpack in a basin, and we see that it's tracking the snowpack very, very accurately, sometimes more accurately than snow models, even though it's never seen snow data. So that's different than ice jams in rivers, which are a big problem. And we do not track ice jams in rivers, just to be very clear. But we do track melting of permafrost. We do track melting of permafrost. That's a different question. But melting of a seasonal freeze-thaw cycles. Okay. The comparison. This is also Mohammed. Thanks, Mohammed, for your questions. The comparison showed between LSTM, Sacramento Soil Moisture Accounting, and National Water Model. Are those events from retrospective analysis using the same forcing data or different sources of forcings? The Sacramento and LSTM used the same forcings. Everything was exactly the same. The National Water Model was different. The National Water Model, we aren't able to run ourselves. We aren't able to, you can't get it from the National Weather Service to run or calibrate. So they just release a retrospective prediction data set that is what it is. And that's why it's fundamentally not a straightforward comparison. But the LSTM and the Sacramento model, we used exactly the same input data, exactly the same calibration periods, and exactly the same calibration data. So that comparison is completely one-to-one. Okay. Is there an API to retrieve the LSTM forecast? Yeah, great question. The API is in alpha mode right now, so it's being tested by a set of trusted users. It will be in beta very soon, weeks or months. And yes, you're absolutely welcome to compare it to. If you really want to run a comparison, Mohammed, the other part of Mohammed's question is, can he get the data to run some comparisons? If you really want to do that, we're happy to share the data. You probably have my email address, but if you don't, Santiago will give it to you, and you can reach out to me and I'll try to get you data to the extent that I can. Otherwise, we can wait just a few weeks for the API to go into beta release and then you can get it. Oh, you can help with, yeah, so do email me about this Tunisia thing. I'd love to speak about it. That's fantastic.
I have another question.
Yeah.
So you're training with a year in the past,
yeah,
and 7 days in the future.
Yeah.
So what happened when like this year is, for instance, El Nino?
Yeah.
So I guess the climatology will change.
Yes.
It's likely. So how does that affect the predictions on this kind of a
Yeah, it's a great question.
events?
So the reason we use a year is to get that whole the whole sort of storage cycle, right? So we don't expect there to be large, other than groundwater, we don't expect there to be large changes in water year to year, right?
Yeah.
There are some groundwater and whatnot, which have some effect on floods. So going back further would be better. But that year is really just trying to catch the vegetation cycle and the freeze-thaw cycle of snow, right? And then also catch the recent history of rainfall. And the climatology differences come in to the model as weather predictions. So El Nino will affect the climate, but what it's really doing is affecting the weather, right? And we get that information by seeing this year's weather inputs are different than last year's weather inputs. That makes sense, yeah. Okay, so Tao says, what are your ideas about the LSTM application in streamflow prediction in arid areas with relatively poor performance? How do you plan to improve the model to collect more data? That's a fantastic question. So arid areas have several problems. One of them is this sort of dependence on high uncertainty rainfall. Another of them is that the timescales at which floods happen in arid areas are much shorter. And so one of the things we're doing is we have in our team is we have a flash flood prediction project. And the way that we model that is quite different. We don't actually try to model the rainfall runoff relationship. Basically, the strategy is to create a base map of risk. So saying this area just in general has higher risk of flash floods than this area over here. And then the algorithm then is to bring in the rainfall forecasts, add it to that base risk map, and then predict a probability of a flash flood occurrence in that particular location. So there's no like dynamical modeling in that situation at all. And that's basically the way that we're currently attacking this problem. Why does it not show for Ethiopia? We wanted to compare with the locally developed flood early. Oh, that'd be amazing. Tedla, sorry if I pronounce your name wrong. That would be absolutely amazing. And I really invite you to contact me. We would love to do that comparison. Also, we would just really like to speak with the people that developed the flood early warning system in Ethiopia. That would be phenomenal. Please get my email and reach out to me. That's fantastic. How are we accounting for uncertainties, weather uncertainty, and what thresholds of confidence are you considering to consider a reason high risk region? So what our model is actually probabilistic. I didn't talk about that, but the output of the model is not actually a prediction of stream flow. The output of the model is actually a set of parameters that define a probability distribution over stream flow. That probability distribution changes at every time step and every location. So the model actually predicts a set of parameters that define a mixture density function that then is the loss function that we use for training is the negative log likelihood function of that mixture distribution. So from that mixture distribution. So all of the uncertainties, we don't explicitly consider uncertainties in weather inputs, but all of the inputs come in, all of the and then what comes out is a probability distribution, is the model's best estimate of the predictive uncertainty based on how it's seen rainfall runoff relationships in the past. So we do predict probabilistically. There's more work to do there. I think your idea about actually explicitly accounting for weather uncertainty is great. Like one idea there could be to add a variational layer, a variation autoencoder layer on the inputs to the LSTM and have that kind of learned distributions related to the input data, that would be phenomenal. We just I haven't had time to do it. That's a really good idea. Yeah, so Abdallah says, do you think there is value that might have been lost by using lumped data as opposed to spatially distributed data? The answer is maybe. So there's a group, a private company in the United States that does spatially distributed modeling with these LSTMs, these CNN LSTMs. And my understanding of what they've reported, although I'm not an insider there or anything, but my understanding of what that group has reported is that they get value from the CNN LSTM when they use satellite data of snowpack. So understanding, just having that satellite data of where the snow is in the watershed, how quickly it's melting, what parts of the watershed is melting, what elevation bands are melting and which are not, which are accumulating, that's valuable data for the model. I don't particularly know the answer to that. The challenge that we've had using spatially distributed models, and it's spatially distributed here in the sense of within a single watershed, not spatially distributed in the sense of how watersheds are connected with each other to form larger rivers. That's a different problem. But spatially distributed in the sense of within a single watershed, the main challenge there is watersheds are all different shapes. So you're going to have to come up with something really clever to make a model that generalizes from one location to another. So that learns on a whole bunch of watersheds that have a whole bunch of different shapes, and then is able to predict on a whole bunch of watersheds that have a whole bunch of other different shapes. So it's a solvable problem for sure, but that's the problem here, the main problem that I think you're going to have to solve. Tadella says, how can we utilize the developed forecasting platform for ungauged local watersheds? Oh, yeah. Again, please contact me. That's fantastic. Let's see. Dubu says, again, I really sincerely apologize if I'm pronouncing your name wrong. Dubu says, how can we effectively quantify and reduce uncertainty in the LSTM? Yeah, it's a fantastic question. So, I think what I would say is we just got back from the science conference in Vienna, Austria, Earth Science Conference in Vienna, Austria last week. And there was a lot of work on people understanding how to improve these models. And, there's just a lot of little tricks that you can do. It's a great machine learning problem. It's a fantastic problem to jump in and learn machine learning for graduate students. It's a problem with a lot of room for improvement, a lot of potential overhead. And yeah, I don't have any specific answers for you because if I did, I'd try to do them if I had time, but there's a lot of overhead here. There's a lot of interesting problems here. Yeah, transformers, Dubu, transformers versus LSTMs. I actually almost showed some slides. Actually, let me go further in my deck, and I have some slides about transformers. Oh, I messed up. I put stop sharing instead of stop presenting. Okay. So we've built transformers for this problem. So this is my slide deck that talks about transformers. Since you're asking about them, I know that you know what they are, but and I don't have a direct side-by-side comparison, but what I do have is this plot, which is really cool, which shows how the different self-attention layers. So we have parallel and stacked self-attention layers in the encoder portion of a transformer. And what we're looking at here is sort of the attention maps, the attention maps for in these layers. So this is the layer 2 of a 2-layer forehead. So this is the second layer of a forehead self-attention encoder. And this is really hard to go through. It's going to take a lot of time to go through this, but so I'm not going to go into detail. But basically, what I'm going to say is the model is able to learn, the transformer model is able to learn what I call hydrologic grammars. So it's able to learn different patterns of memory in the different heads. So 4 heads means 4 parallel self-attention networks. 2 layers means 2 deep. And these 4 parallel self-attention layers learn different relationships between the input within the input data. So again, I really don't want to go through the details of this plot, but basically one of these heads is looking at the past, all the past weather data, not anything in the future. So the y-axis here is the time from the y-axis here is the 365-day look back. That's the 365-day warm-up period. And the x-axis is the day of simulation. So what you see is these diagonal bars, meaning the diagonal bars are, it's there's some usually precipitation event that's important to forecast stream flow. And as you go forward in time, that becomes one day further in the past. So you get these diagonal bars that represent sort of the attention maps. And you can see that there's one of these heads is learning seasonal pattern that focuses on the recent weather data. One of these heads is learning very recent how to deal with very recent weather data. So not seasonal, but just how to combine the immediate weather data. One is learning how to deal with strong precipitation events. So what you're seeing in this number 2 head here is these diagonal bars representing really strong precipitation events. So this head is kind of learning how to deal with really strong precipitation events. This head is learning how to deal with very recent meteorological combinations of meteorological data, and so is this one, but also with some influence from precipitation. So the long story short is that we can train transformers, and we've gotten them to about 1 to 2% of the skill of the LSTMs. So they're almost as good as LSTMs, but not quite. At least we haven't gotten them to be quite as good as LSTMs. And I'm sure that someone could go in and improve that, but that's what we've found so far. Again, the reason we like LSTMs for this is because they're well matched to the problem. Yeah. And then I think the last question from John is, do you ensure that the different data sources have the same resolution? The answer, kind of and kind of not. So the different data sources definitely don't have the same resolution. That's for sure. All the data sources have different resolution. But what we do is we do an area weighted average over each watershed. So we're actually taking one value from each data source for each watershed, and we construct that value from whatever native resolution the data product is in by taking an area weighted average of the sort of geographical overlap between the watershed polygon and the pixels of the data product. Cool. Yeah, and so, Abdullah says, where do you see the future of process-based models for stream flow forecasting? Dubu, I'm skipping yours because just get in touch with me by email. We can talk about this by email would be great. Again, let me just put my email on the screen since I've said it so many times here. Let's see.
I think John.
What's that?
Oh, yeah.
John, cool. Oh yeah, John. Go ahead, John.
Yes, I thought this might be better if I asked it this way. So looking at the performance, what do you say comparing Africa to the other continents? How is the performance and what would be the cost?
That's a really good question. Let me actually, I can actually show you the answer to that question, but let me see. Let me put this up and I'll come back to it. I want to see if I can find the correct graph to show John the answer to that question. Let's see, 1 second. So, yeah. So this is the paper that we published, and then if you go into the extended data, no, not even extended data, it's in the regular paper. Yeah, so we get this plot that shows sort of average skill distributions over different continents. And this is kind of the distribution of skill scores between the blue model, which is the current GLOFAST system, and the orange model, which is our current our machine learning based system. And kind of the thing that you want to see is that there are differences in continents over 1 year, 2 year return period scores, 5 year return period scores. There are large differences among continents, and that has our sort of working hypothesis is that has more to do with climate than with anything else. So again, it's more the driving factor of the skill scores in these predictions are whether it's an arid or a humid climate. That's really the driver of the skill score. So that's we think, we don't have proof of this, but we think that that's what's driving these differences in skill scores across the different continents. The one thing that I would add that I think is kind of cool, if you look at like 1 year return period events, this is what I'm about to say is not too true, but if you look at 2 year return period events, our skill in Africa on average is about about the same as the skill in Southwest Pacific. It's slightly better than the skill of GLOFASS in North America, for example. So that's not always true. You can see our skill for 1 year return period events in Africa decreased a little bit compared to the state of the art, but most of the time we get a pretty nice increase. And actually, again, 2 year, I think for 5 year 2, the skill in Africa from our model is actually on average better than the average skill in North America from the GLOFASS model. So those are the kinds of improvements we're seeing continent to continent. Yeah. Does that answer your question? Thanks.
Well, if this is what you've observed, that's fine with me. But wouldn't you think data availability and data quality is also a contributing factor?
Yeah, absolutely. So first of all, sorry, I said climate's the most important thing. Climate's the most important thing for the results of this study, but data availability is far, far more important than climate. But you don't really see that effect in these results because these are sort of cross-validation results. But having data available in an area in similar types of basins, having data available in an area in hydrologically connected basins so that you can kind of learn patterns in the specific river network that you're working in, and having data availability in the actual area they're working in that's transformative. That's the most important thing in the world in the whole game that we're playing here. And the one thing that's worth saying about that is we and me specifically, I spend most of my time looking for partnerships that will allow for data exchanges. So for us to get streamflow data and for people to use our model prediction data. So we're very interested in building these types of relationships where we can, we can train on more streamflow data and where we can provide partners with our model predictions. And so I'll just put that out on the table.
Okay, thank you.
Yeah. We are a bit over time, but I think we can take a Gojo question and one other question from the chat.
Yes, sir. Thank you very much for your time. Actually, I wanted to ask a question in line with what my colleague just asked right now. I was thinking on more data reconstruction because reconstitution, sorry, because it's really hard in Africa mostly there are a lot of engaged basins where we don't have stream flow data mostly. I was thinking more utilizing this model if you can reconstruct the data, to get historical data, and maybe that we could use for further analysis.
Yeah, absolutely. So I think the thing that I would say to that is we will have this expert mode in Flood Hub coming out in the next, I don't know, this year, next month, next 2 months. And that will allow you to pull our predictions everywhere in the world, geographically dense locations. And if you want, if you or anybody wants to use those predictions as if they were reconstructions, I think that's a fine thing to do. I think that's appropriate. Just as long as you understand it's a model, just like any other model. Models aren't reality, but they can be used to inform about reality, as you know, I'm sure.
Well, so the last question from the chat, Amal is asking if there's a lot of regions mainly in Africa that are missing in the Flood Hub. I think mainly due to geographical bias you have in the model. Do you have future plan to improve the model and include these regions, basically create a global model?
Yeah, absolutely. So again, the Flood Hub that's sitting here right now is only gauged locations. So these are only locations with streamflow gauges where we can actually compare the model predictions to the actual observed data on the ground. And then we only show even a subset of those locations where we've approved the model performance. So again, we'll have this expert mode of Flood Hub, I think in May. I think it's coming out this month, where we'll have predictions everywhere. And so I do apologize for giving this lecture just a little bit prematurely, but this sort of full, dense geographical coverage is coming this month, or certainly next month if we don't get it out this month. Yeah, we have a major launch coming in May.
Yeah. Well, the last question is if we can have a technical section on about how to configure LSTM for flood forecasting, but I think I can talk with someone from the floods team to give like such a section, maybe in a future seminar or something.
Cool.
So, yeah, thank you very much.
Awesome.
So yeah, well, I don't know. I'm not really good at closing the stuff.
Awesome. No. Yeah. Thanks, everybody. Really appreciated the opportunity to talk, and it was nice to virtually meet you all. Thank you.
Yeah, thanks.